My talk with a bug. This is not the LUC conference, this is a LUT conference, so it was just a copy and paste bug. Hopefully this is the last bug. I will take the opportunity to, Lustre you all know, but maybe only few of you know what is GSI and what is FAIR. So I will take the opportunity to explain what we are, why we are using Lustre and what the hell we are doing at GSI and what means FAIR. So GSI is a particle accelerator lab, so we have a particle accelerator, and FAIR is our new project. Okay, thank you. So FAIR is a new project, is a next generation accelerator. FAIR means Facility for Antiproton and Ion Research. I will come to this later. So let's have a look to what kind of physics we are doing. Next page is like this, okay. So you should not afraid because of physics. So the first question is why we spend another billion or more than $1 billion of tax dollars for a new generation of accelerator. You all know there is LHC at CERN, so why the hell we need a new accelerator? So LHC is in a region which is located in a landscape of temperature and net baryon density. LHC is a little bit in the corner of the Big Bang, so quite hot and normal baryon density. The new FAIR accelerator will be deeper, penetrates this region, which is here indicated with deconfinement and chiral transition. If you're interested in chiral transitions and deconfinement, ask me in the coffee break. I will not go into detail now. The important point is we will reach much higher baryon densities with the new accelerator. This is one of our key features why this accelerator is built, so much higher baryon density. And there's another argument for the new accelerator. By the way, this is the existing GSI. Blue is the existing LINAC, and this is a synchrotron. And red is currently under construction. This is the next generation accelerator. The F from FAIR means facility because we have lots of experiments here. And CBM, condensed baryon matter experiment, is which are dealing with quantum chromodynamics, going to high baryon density, studying the physics in these fields. And in general, the second key feature of this accelerator is high luminosity. This means there's lots of, it's not only energy, luminosity is particle density in the beam. The particle density is so high that we can investigate the production of very rare events. And on the other side, the primary intensity is so high that we can convert this beam into an antimatter beam. And with this antiproton beam, so we have a beam of antimatter. With this antiproton beam, we can study with another huge experiment, PANDA, we can study quite exotic reactions. So these are both of the main arguments why to build a new accelerator generation. So, and now what you're seeing is this is the existing GSI. This is a new accelerator infrastructure. It's not only plans, so there are really some yellow machines on the field which are drilling holes and filling holes with concrete and steel. So there's some activity going on. First light is to be expected in 2018, late 18 or maybe 2019. So it will take some years to see first light, but we have an enormous amount on computing to realize this project. This you will see on the next transparencies. There is something more new in connection with the accelerator. So first of all, I'm talking about I will not give a complete overview over all of our experiments. So I'm focusing on two of the experiments I mentioned. This is the condensed baryon matter experiment and the antiproton experiment. They will deal with about 1 terabytes of data per second. So one experiment, 1 terabyte per second, Panda about 0.5 terabytes per second, and then all the other experiments in addition. So this is an enormous amount of data. Traditionally, in the past, this amount of data per second were handled to build so-called hardware triggers, which select from this waste of data, they select with hardware methods the interesting events. The disadvantage of this approach is there was no other choice, because you cannot deal with such an amount of data. So the hardware trigger approach has a disadvantage. There is some pre-justice in the physics. If you build your hardware trigger, you know what you have to expect from the physics. So with this new accelerator, we want to be completely unprepared for everything what will come. We will be prepared for everything what will come. So we build, instead of building in hardware, we make something like a flexible event selector. So it's a huge compute farm. Per experiment, we expect about 60,000 cores. So these huge supercomputers will, on time, reduce this amount of data to something which we can handle. So after the flexible event selector, we expect 1 gigabyte per second per one of the experiments. So even Panda will deliver then 1 gigabyte per second. This is a region where now Lustre come into in the game, because once you detected that, once you see some very rare interesting event, you have to reprogram the flexible event selector and focus on this new discovery which you have to reconstruct your trigger online. But to decide for this decision, you need a very fast analysis, and you have to analyze a vast amount of data immediately. So we need a large online cache which can keep an amount of data in the many petabytes era to make these decisions as fast enough. So this is big data, and for this we are prepared with Lustre to do this. Now I'm talking about our existing Lustre system, which is in production. So this is now not science fiction, this is production of our current Lustre. We are using Lustre for analyzing the already running LHC accelerator experiments, for example, ALICE, the ALICE experiment. Of course, we are analyzing our own experiments at GSI, for example, HARDES and other experiments. We have some simulated data for the FAIR experiment, so we have ongoing simulations for the design of the detectors of this new generation of accelerator. We even have lattice QCD for the FAIR physics and accelerator physics, of course. There is a difference between accelerator physics and lattice QCD, for example, and this kind of type. So the demands of this is more latency. So this is latency critical, especially lattice QCD calculations. But the amount of data is, the IOs which you can handle is in the normal field. The LHC experiments and GSI experiments is very high demanding of IO. So IO is a key feature. And to tell you this, because we had Lustre at GSI many years ago, most of our analysis was just IO bound, because we had enough computer cores, but the whole analysis was stuck due to the demands, the IO demands. This is now past. We have solved all these problems with Lustre. So from the numbers of our production system, it's about 7,000 disks. It's quite more. We have about 10 petabytes cross capacity, including RAID 6 and global spare. So if you go for what is for the user, you end up with about 6.5 petabytes for the users. And the whole machine is optimized for high I/O. So we have 2 terabits per second I/O capacity, which we need for our experiments. So this is a special machine dedicated for really high I/O. So short summary, built at HPC department, so the whole cluster is done by ourselves. So there's no big vendor involved. It's built on commodity hardware due to cost reduction. And so overall, it's successful. The analysis is no longer I/O bound. It's reliable, stable, fast, at least reliable and stable. The Lustre 1.8 series, so 1.6 was not so stable. And the whole stuff is built inside a prototype of the mini cube. I will show you later what does this cube stuff mean. So here's a little topology of our cluster. We have two main clusters in Lustre. Hera is InfiniBand based and capable to do the latency critical stuff, including the lattice QCD, and the Ethernet based, a little bit older Lustre, which is connected with an Ethernet number cruncher cluster, and Prometheus is our InfiniBand number cruncher cluster. Both Lustre are connected via gateway clusters and LNet routers. Of course, there is a connection to a library and a cache system, which is named GStore, which will be maybe in the future Lustre 2. And a special point I want to show you, there is a LNet router cluster, which go to TerraLink. TerraLink is a new experimental project which we have at GSI, and I will show you what is already in production. TerraLink will connect the local, let's say less than 200 kilometers away from GSI supercomputers and computing infrastructure and universities which are contributing to FAIR. FAIR is an international project, but the computing will be done in a tier level style, and the tier 0 center, which contains most of the data, will be located at GSA and in the surrounding, and this will be connected together with cross-Lustre links. And we already have a prototype of this Terra link. Terra means we want to achieve terabits per second in the next years. We already have reached 120 gigabits. So this is now connecting Hera, our InfiniBand Lustre, via about 85 kilometer glass fiber to the Löwe supercomputer in Frankfurt. And the connection is done, so it's a Lustre connection. The Lustre clients are at Löwe supercomputer. We have Lustre clients, and Hera is at GSI. We have not only Lustre clients, we have the object storage servers, of course, and this is a 10 petabyte stuff. And the connection is done via a cluster of 12 LNet routers. On the Hera side, they have InfiniBand interfaces. At the other side, they have 10 gigabit Ethernet, because we do the 85 kilometers with Ethernet and glass fibers and do the transformation with the LNet routers. And okay, this is topology. The question is this working or not? And the funny thing is it's really worked. So it's already working, it's in production. So we have Lustre clients at Gauss supercomputer in Frankfurt, which accessing Hera at GSI. And 12 LNet routers with 12 10 gigabit links mean you can estimate from theoretical point of view, you should achieve something. So the theoretical bandwidth is something like 14.5 or 15 gigabytes per second. And we reach in reading and writing numbers which are in practice, which are close to the theoretical bandwidth which you can achieve with such an Ethernet connection. So it's working. So now this is all these flags as FAIR is an international project. So it's European countries, but even India, China, and other countries. What we plan is to connect now. This is the existing connection to Goethe University and to the Gauss supercomputer. And what we want to achieve in the near future is a metropolitan HPC system, which is connected to the central Lustre cluster at GSI and have Lustre clients in the area. So Gießen is about 150 kilometers away. So it will be in the some 100 kilometer range cross Lustre connections. And we want to achieve 1 terabit per second. We already have achieved 120 gigabit per second. So, new developments. I want to bring your attention to, of course, we have now to deal with some security issues because we are connecting different sites. So there was in history, there was a Kerberos implementation of old Kerberos RP with Lustre 1.6, I believe. So meanwhile, there's something changed. So we are working on some bug fixing with Kerberos, and we have built some own kernel security module for Lustre. There will be a talk of Thomas, I believe in 1 hour, something like this. So all details, ask Thomas. And of course, we have all our changes are published. So what we do in the future is some testing with Lustre 2.4 HSM. So I'm sure we want to contact CEA for this. Clustered MDS, ZFS. With ZFS, we have already some experience. Looks promising. So we are going into this direction in the near future. And so this was now the production system. Now what will bring us the future of GSI for GSI and FAIR? So we will have to run about 300,000 cores. This is our estimate for the start of the FAIR experiment. We would estimate about something like 50 petabyte as an online cache for immediately analysis of the data. And this should be done with Lustre. Maybe we will use a cache cluster for interfacing the long-time storage. Maybe a good solution for this would be even Lustre. We have to investigate. Completely unclear is how we do our persistency because we will produce enormous amount of data. Now everything is based on tapes. I do not know what will be the technique in 4 or 5 years. Are there still tape drives available? I do not know. In the past, every 5 years, the people claimed that the tape drive will be dead in the next decade. It never happened. So, but I'm not sure if the tapes will survive. Maybe a Lustre with something like, this is fun, of course, RAID 8 is not existing, but maybe a very high RAID level together with spinning disks or SSDs or some technique available or cheap in some years could do the job for long time storage. So I have 2 question marks after this project because we are not sure how we go in the future. Maybe we just keep our tapes. So now you can think about 300,000 cores and tape libraries and all this stuff. It should be located somewhere. What we have is a green IT cube concept. By the way, this is an award-winning concept because this is a first data center with a real 3-dimensional structure, by the way, with very high power utilization efficiency. So we have prototypes which reach 1.06 or 7, so only few percent of the power we need to power the computers we need for cooling. So we got some awards for this, and this is a principal design. The advantage of such a cube is that especially if you have latency critical or InfiniBand connections, assuming Lustre will be in the inner core, connected to all the analysis farm inside. In such a 3-dimensional array, you can optimize the cable length, which is critical. Even if you look for the cost for InfiniBand cabling, everything will be easier if you have not too long cabling. So this is our concept for the future, and but we will for the near future. So we are in the final planning for this cube. The cube will be built next year. So this is a location at existing GSI. This is a cube, something like 25 meters in each direction, and contain lots of spaces for all the cores, as you can imagine. The special part of this concept is we will use waterfalls for cooling. So it's a completely passive cooling. It's the only way you can achieve a a PUE value of something about 1.06. You never achieve such a power utilization efficiency with some active cooling. So this is not just science fiction. So we already have at GSI a working prototype, which I will show soon. We reach the design value of the PUE, and we survived even the hottest summers. We survived with this cooling stuff. The trick is it's just plain physics, because evaporating water makes a lot of delta T. So even if let's say the outside temperature is 32, 33, which we reached this summer in Darmstadt, the cooling water is something like 26, 27 degrees, because due to this evaporation cooling of the waterfall, and inside these cabinets we have special water-cooled cabinets of a special design, and we can drive this cooling with a delta T of less than 1 degree is sufficient normally, or something like 1 degree is sufficient to cool down. So with 27 hot water inside, we have 27.5 or 0.8 warm water going outside. So this small temperature difference is everything which we need. So the cooling inside is just the temperature which I reported. So we can run this quite cool, even if the summer is hot, at a really extremely good PUE, and the trick is this waterfalls in combination with the cube design. So this is my last transparency. Unfortunately, you see not too much. This is our mini cube. Maybe you will detect something odd because the bottom is shining with light. So it is not that we have too much money to illuminate the floor of our data center, because this is already a working prototype, the production prototype of our 3-dimensional cube. So what you see here is the light of the level 1 minus 1, which is coming upstairs. By the way, these are the people which do all the work. This is the HPD department, at least some guys. Okay, thank you. No question to chiral symmetry?
So as you're building your Lustre infrastructure yourself, what tools are you using to monitor for reports and things like that?
There was a very nice talk from CEA. We're using this guy in front of the computer, which is blinking all the time. Of course, we try to use Robinhood, for example. The problem is we are still running the 1.8 series. We have 100 millions of files with 250 million inodes. So you could estimate from the numbers which we heard from CEA, we would need days, some days or a week to make a full run of this. But unfortunately, it breaks after 1 day with the LBUG. So maybe this is a good opportunity for co-work, because we want to look inside, because this to check everything is a nightmare. And these crazy people we have at the first, as we introduced Lustre many years ago, the first thing what our friends from the experiments discovered was a huge space empty where can be filled with files, and they put in one directory whole experiments inside. They even reach the limits which POSIX can deliver you to remove or to handle files. So we are interested to make this a little bit more automatic. So we would be interested to make Robinhood running at our site, and even to make it running together with a cross-site monitoring. So we are just now in the phase of developing even cross-site monitoring.
You mentioned that you guys are working on some Kerberos fixes. There seems to be a number of people that are doing similar things. Is there are you coordinating with anyone else about your changes and their changes and anything like that?
Thomas will go into the details. So what Thomas did is a security module. He will present this, and the Kerberos fixes are reloaded to Git, of course, so everybody can look inside. And it would be nice if we had a coordination of this. Yes.